Can you see my screen?
Yes.
So I guess you can also see this bar on the right. I'm not sure how to, okay, I'll just move it if needed. Okay, so I'll talk about multiplayer bandit learning, and I'll discuss several aspects of this, in particular related to whether the players are competing with each other or cooperating, or they are completely selfish and maximize their own rewards. And this is based on joint work with Yuval Perez. So the setting that I will talk about is as follows. We have two players, Alice and Bob, playing a multi-arm bandit problem. And it's going to be very simple. So one arm is safe, which means that it has a known probability of success P. So if you pull the arm, then you get a reward of 1 with probability P and 0 with probability 1 minus P. And the other arm is volatile or risky, which means that it has an unknown probability of success theta, and we know the prior, which is some mu. And in every round, each player pulls an arm, then it observes the reward at that arm, which could be 0 or 1. And then they look at what the other player did, and they can see the action that the other player took, but they cannot observe their reward. And this is going to be true forever. So the players will never know exactly what rewards the other participants got. So this is an example of what it might look like, well, a trajectory. So for example, here Alice starts at the left arm. In round 1, she pulls that, and Bob starts at the risky arm. And then Alice in the next 3 rounds decides to explore the risky arm, but then she's not so happy with the rewards that she got there, and then she switches left to the left arm, which is safe, and she knows what is there. Bob, however, decides to stay longer at the risky arm, and that may be the case because perhaps his first pull at the risky arm was a 1, so he's happier with it. So to completely define the setting, we have to specify what the utilities are. And the general definition will be that Alice's utility is gamma A plus lambda times gamma B, and similarly for Bob, where gamma A are Alice's discounted rewards. So this makes sense. We actually study both the discounted and finite horizon setting, but I'm going to focus on discounted to make the presentation simpler. So gamma A is going to be the sum from t equals 0 to infinity of the reward that Alice gets in round t. So that's little gamma A of t times beta of t, where beta is the discount factor. And similarly for Bob. So this is the discounted rewards. And what the utility formulation captures is that each player cares about its own reward, but they might also care about what the other player gets. Like they might, if they are siblings, maybe they do have some interest that the other player does well. And we can have a similar definition for finite horizon, where gamma A is the sum of rewards, little gamma A of t, where the t ranges from 0 to the horizon, capital T. Now we'll focus on 3 main settings. So the first is the competitive or zero-sum game, where lambda is -1. So this means that Alice's utility is gamma A minus gamma B, and Bob's is gamma B minus gamma A. So this is whatever a player wins, the other one loses. So they want to they care about the difference. So they care about who comes first, and moreover by how much. And an example of this is basically any zero-sum game, but in a market setting, you could have competing phone companies where they have a saturated market. So a customer that is obtained by one company means that is lost by the other one. In a neutral setting, which is actually the setting that we usually talk as being the selfish setting, so the players only care about their own rewards. So then Alice's utility is gamma A and Bob's utility is gamma B. So each player only cares about its own reward. Then in a cooperative setting, both Alice and Bob have the same utility. So they want to maximize the sum of rewards. And so we say that the players are aligned. And a place where you may see this in the animal world is organisms that are identical genetically, like ants or bees, or almost identical. They're happy to basically do things that are worse for them so that other members of the group are doing well. And you could also imagine a partly cooperative setting where lambda is a half. So let's say if siblings share half of the genes, then Alice would have utility gamma A plus gamma B over 2. So here she wants to collect lots of rewards, but she also cares about Bob. So the strategies are, so a strategy is going to be a map from the history to the next action to play. So what this means, the Alice's strategy is going to be a map from the bits that she collected, the actions that she took, and the actions that she saw Bob taking to the next action to play, and similarly for Bob. And we allow randomized strategies. So, and then we can talk about expected utility, which is going to be computed using the player's belief about the private information of the other player. And to understand what would be first the optimal one-player strategy, we'll talk about the Gittins index, which will denote by G, and it's going to be a function of, so this is for the risky arm. It's going to be a function of the prior mu and of the discount factor beta. And it will be the infimum of the success probability P, where always playing a safe arm with probability P is optimal for a single player. So this can be understood as a retirement value. Like if you have at some point you have a risky arm with prior mu and a safe arm with probability P. And would you be willing to retire at that point, so that forever from that point on you never explore the risky arm again, but instead you're happy to get P in every round. And of course, as you explore more, the Gittins index changes. And I should also know that when G is greater than M, where M is the mean of mu, if mu is not a point mass, then we have the G is greater than M, where M is the mean of mu. And the optimal strategy for one player, which is facing any number K of risky arms, will be that in each round, the player pulls the arm with the highest Gittins index at that point. There is a lot of related literature, which I won't get to cover all of, but I will try to mention several directions. So one is multiplayer learning in the collision model. So here there are multiple players that are pulling arms independently. They are cooperating. For example, they're trying to maximize the sum of the rewards, and they can agree on a protocol beforehand, but they cannot communicate during the game. And whenever there is a collision at some arm, nobody gets anything. Whoever pulled that arm gets a 0. And this has been studied in the adversarial setting or the stochastic setting. And also it matters if the players receive input about the collision or not. So there is also work in economics in the same feedback model as in my presentation. So one is by Ayagi from 98 and also 2011, where there are two risky arms and where the priors have discrete support. And by Rosenberg et al., where they study the same model. So there's a safe arm and a risky arm. And there are two players, but the decision to switch to the safe arm is irreversible. So they studied this for the case where the players are selfish. They purely care about their own rewards. And there is also literature in economics related to research and development, where the interplay between competition and innovation is modeled with bandit learning. There is there are also multiple papers that study the same model with the exception that the feedback is immediate. So the players decide what to play. They don't know exactly what the other player is doing in this round, but then in the next round, they see all the bits collected by the other players. And in the setting, so there is no accumulation of uncertainty in some sense. So there have been observed like free rider effects and encouragement effects, where a player may explore in order to encourage further exploration from others. And then there is also a theme of incentivizing exploration, where there is a platform or a principle that has a number of arms that they want to explore. And the only problem is that exploration is done by a stream of myopic agents that show up once and then they leave. So they want to do the best for themselves. They want to pull the arm with the highest mean, but the principal is trying to get them to explore more. So one more theme that is related to the paper is from evolutionary biology, where the question is, how did cooperation evolve in animals, and in particular in insects, like ants and bees, where extremely high levels of cooperation were observed. And an explanation is that they're very similar genetically. So I'll start by discussing the competitive setting. So remember here, the Alice's utility is her rewards minus Bob's rewards, and similarly for Bob. So this is a zero-sum game, and it can be shown to have a value by a Minimax theorem due to C1. And the question then is, how do competing players behave? Do they behave the same as a one player playing optimally? Do they ignore each other and they just pull the arm with the highest Gittins index in each round? Do they never explore? So the first theorem will say that competing players explore less. And to make this precise, suppose that we have arm L. It has a known probability of P, and arm R has ID rewards with some unknown success probability P, which has a prior mu. And we know that this is not a point mass. So I don't know if you can, I hope you can see the slide. So now we assume that Alice and Bob are playing optimally in this game, in the zero-sum game with discount factor beta. Then there will exist a threshold P star, which is strictly less than G, where G is the Gittins index of the risky arm, so that for all probabilities P greater than P star, with probability 1, the players will not explore the right arm. So the right arm is the risky arm. And we can also, in fact, say that P star is less than M beta plus G over 1 plus beta, where M is the mean of mu. So to show a visual depiction of this, so here it's the interval 0, 1. A little m is the mean of mu, and the m star is the maximum in the support of mu. We have G is the Gittins index of the risky arm, so the arms are here with probability P and mu. And there is some P star which is strictly less than G, so that in the whole red region from P star to 1, competing players do not explore. So basically, they're happy that, to leave money on the table and to play the safe arm instead. And here we see the region where one player explores. So one player explores in the region from 0 to G, and competing players may explore from 0 to P star, maybe, we don't know. But they definitely don't explore from P star to 1. So there is the red interval from P star to G, where one single player playing optimally explores, but competing players do not explore. So now the first theorem shows that information basically has less value in the zero-sum setting. And the intuition for why this happens is because the players can copy each other. So maybe Bob wants to explore, he starts pulling the risky arm, but then he discovers some gold there, and he's very happy, he keeps pulling, but then Alice notices that Bob is pulling the risky arm, so she infers that he must have found something very valuable there, and then she starts pulling that arm as well. So the players can try to hide this from each other, but so theorem 1 shows that they will in fact be more risk averse. And then a follow-up question is, so will they explore at all? Or are they going to be completely myopic? And theorem 2 shows that competing players are not completely myopic, so they will, so in the same setting as the previous theorem, there will exist a threshold ptilt, which is strictly greater than m, where m is the mean of mu, such that for all p less than ptilt, with probability 1, the players will explore the risky arm in the initial round of optimal play. And we can also obtain a bound for ptilt, which is, so it's greater or equal m plus beta w over 2, where m is the mean of mu and w its variance. So to get a visual depiction of this, we have again the interval 0, 1. G is the Gittins index of the risky arm. So we have P star to 1 is the interval where competing players do not explore. And now we get that there exists some P tilde, which is more than M. So that strictly more than M, so that in the interval 0 to P tilde, competing players do explore. So they explore less, but they still do explore. They're not completely myopic. I will also discuss the cooperative setting. So there I said that the players aim to maximize the sum of their rewards and they can agree on their strategies before play. So the theorem here is that cooperating players are going to explore more. And the intuition is going to be that basically they, because they care about the well-being of the other player, they're going to explore even above the Gittins index, because even if they suffer, that information will be useful for the other one. So they're willing to incur a loss for themselves. So here, suppose we have again Alex and Bob. They have aligned interests, so they maximize the sum of rewards, and they play one arm bandit problem with discount factor beta. We have again the safe arm with probability P and the right arm with prior meaning. And then we obtain that there exists, oh, this should not be P tilde, I'm sorry, this should be P hat, which is strictly greater than G, where G is the Gittins index of the risky arm, so that for all P strictly less than P hat, at least one player will explore the risky arm of positive probability under any optimal play. And by optimal play, I mean any pair of strategies that maximizes the total reward. And to make the connection with biology, basically, for example, an ant maybe could be squashed, like if she searches for food, but if she does find food, then that could feed the whole nest. So that could make them more risk-taking. And now to add to the picture, so this is the intervals from 0 to P hat, where cooperating players explore. So you can say that they explore even above the Gittins index. And I want to say a few words also about the neutral setting, where the players, the utility of each player is their own reward. How much time do I have left?
10 minutes.
Okay. So, so the solution concepts here will be Nash equilibrium and perfect Bayesian equilibrium. So we'll say that player's I strategy sigma I is the best response to player J, which is playing some strategy sigma J, if no strategy sigma I prime has a higher expected utility against sigma J. So basically, player I is doing as well as possible against player J when it plays the best response. And we say that the mixed strategy profile sigma I, sigma J is a Bayesian Nash equilibrium if sigma I is the best response for each player I. So these strategies may be randomized. And then we'll also look at perfect Bayesian equilibria. So perfect Bayesian equilibrium is the version of subgame perfect equilibrium where we deal with incomplete information. And we say that a pair of strategies, sigma I, sigma J is a perfect Bayesian equilibrium. If starting from any information set, subsequent play is optimal. And beliefs are updated consistently with Bayes' rule on every path of play that is explored with positive probability. So to understand better the difference between these, it's relevant to consider the issue of threats and non-credible threats in particular. So for example, a Nash equilibrium might have that both players are behaving really well, they're taking risks when they expect each other to take risks. But what can support that behavior is that one player, if one player misbehaves, then the other player threatens to respond really badly. And so the first player won't misbehave in the first place. So perfect Bayesian equilibrium rules these threats that are not credible, rules them out, because the reasoning is that when you get to that point in the game, actually the player that promised to retaliate doesn't really feel like it. He or she is going to lose their rewards. So both are very much studied. And so perfect Bayesian equilibrium is a refinement of Nash equilibrium. And it's also known as subgame perfect, but this takes into account the issue of incomplete information. And now the question again is, so neutral players, this is really close to the one player setting. Are they going to play just like one player and they will maybe ignore each other in each round and just pull the arm with the highest Gittins index? That's one possibility. So that turns out to be false. So neutral players learn from each other. And to make this precise, so we have again the players Alice and Bob. They maximize their own rewards this time. And then we can say that in any Nash equilibrium, there are two things that happen. So first, for every P strictly less than G, where G is the Gittins index, with probability 1, at least one player explores. And moreover, it's also possible to quantify the probability that the player doesn't explore by some time. So the probability that the player doesn't explore by time t decays exponentially in t. And if we further require that the equilibrium is perfect Bayesian, we get that the players learn from each other. So suppose that we have the P, so this is the success probability of the safe arm, is between P star and G, where if you remember, P star is the threshold above which competing players do not explore. So if the equilibrium is perfect Bayesian, then every neutral player has expected rewards strictly higher than a single player using an optimal strategy. And the intuition for why this happens is that the players can basically let each other take turns exploring. So neither of them will incur as high of a cost for exploration. And now to complete the picture here, so we can add the interval P star to G where neutral players learn from each other. So this is for some phenomena that happen in this setting. I want to say a few words also about the very long term. So we don't know exactly what these strategies look like. We know that they explore more or less than one player playing optimally. But we want to think about also what happens in the very long term. What do their strategies look like? And this issue was considered by Rothschild in economics. So Rothschild in '74 studied a single person two-arm bandit problem and showed that the player ends up on the wrong arm with positive probability. And from that, he conjectured that two players that are playing this game observing each other's actions, may settle on different arms. So each arm has some prior. And what was the kind of reasoning behind this? So, for example, if a single player can end up on the wrong arm, this is because he will give up on the good arm if it happens that he has bad draws on that arm. So now, even if there are two players, it could be the case that, for instance, when Alice settles on arm 1, Bob settles on arm 2. Whenever Alice pulled arm 2, she got unlucky. She got some bad draws there, so she left. Similarly, when Bob tried Alice's arm 1, he was unlucky as well. So they conclude that they're playing the correct best arm and the other player is wrong. In a paper in '98, with a follow-up in 2011, Ayagi showed that this is actually not the case. So he showed that when the two arms have discrete priors, the players will actually converge. They will settle on the same arm in the long term. Rothschild, I should also mention, gave an example from pricing. So you could imagine two stores that have different pricing strategies, and each store thinks that the other store is wrong because they have some data that is different from what the other store has. So there is a different point of view, is that if we think of agreeing to disagree, there is Salmans' agreement theorem, which says that rational players with common knowledge of each other's beliefs cannot agree to disagree. However, the bandit setting is different, so it has some elements that are not found in the setting of Salmans' theorem, which is that players keep getting different information, and this uncertainty accumulates over time. So if Rothschild's conjecture is incorrect, then it would be like a version of Salmans' theorem for this setting. I want to give an example for the long-term behavior, and I'll start with aligned players. So these players maximize the sum of rewards, and I'm going to look at Nash equilibria. So actually here there is a Nash equilibrium where they do not settle on the same arm. One player keeps alternating infinitely often between the two arms, and this is this is the example basically, but the actual example is here. So basically there is a schedule. So Bob's strategy is that he has a schedule. So you can do this for any discount factor. So we'll pick some integer k. And what Bob is going to do, he will play the left arm here in round 0k, 2k, 3k, and so on. And then he will play right on the remaining round. So you can see what he's playing with blue. And now Alice's strategy is to play right forever, but forever means as long as Bob follows the strategy above. And then if Bob ever deviates from the strategy, then Alice switches to playing left forever. And now you can show for a choice of P, and so M is strictly greater than P. You can show that this is a Nash equilibrium. So even though the players are maximizing the sum of rewards when they're playing a Nash equilibrium, which has this feature of non-credible threats, which basically leads to a flaw in their execution. And no player can do better, can get a better total reward by switching by themselves the strategy. We do show, however, that for competing and neutral players, they settle on the same arm. So if you have Alice and Bob, they're in the same setting that we discussed. So the left arm has success probability P, and the right arm has some prior mu. Then in any Nash equilibrium, the players eventually settle on the same arm with probability 1. So this is for both competing and neutral players. And the intuition is that if both players explore finitely many times, then we are done. So by explore, I mean that they pull the risky arm. So if both settle on the safe arm, then there is nothing to prove. Otherwise, there will be a player, suppose it's Alice, who explores infinitely often. And then Alice will end up knowing which arm is better because she is at the risky arm a lot. And if she continues exploring, this does in fact mean that theta is strictly greater than p. So theta is the parameter of the risky arm, the success probability. And now Bob can't exactly tell what rewards Alice is getting, but he sees that Alice keeps exploring. So that means that he will eventually realize that theta is strictly greater than p, and he will join her at the risky arm. So there is a challenge about the time where this happens, because theta might be very close to p, which can delay the time where Alice determines the risky arm, the better arm herself. So there are some open questions. So one is whether competing and neutral players always have optimal pure strategies, or if randomization is required. So we didn't say a comment on what their strategies look like from this perspective. What about the setting of multiple risky arms? Are there optimal pure strategies, like in the same way as there is a Gittins index for one player? It would also be good to know if p tilde is equal to p star. So there was that dot between p tilde and p star. It's actually not clear they're equal. They probably should be equal. That would amount to showing a form of monotonicity in the setting. This model could also be used to model pattern protection, like if a player learns the other player's rewards but with a delay of k rounds. Or you could imagine giving a pattern, like if the first player who explores an arm can explore it by themselves for the k rounds after its first exploration. There are some other questions, like when there are multiple risky arms, do neutral and competing players eventually settle with probability 1 on the same arm? So for neutral players, this will settle Rothschild's conjecture. And finally, there is an issue about computation, so I didn't say much about that. For example, if the players have finite memory, so in the discounted game, players need to have unbounded memory that it grows more and more. So what if they have 100 bits that they can remember from the past? What kind of strategies would they play? So I'll stop here.
Thanks, Amina. So now we're just going to open the floor to questions for our three speakers. I think Yonju is not here, but I can answer questions on this talk.